Good morning, everybody. Sorry, but that I do not feel very good. That's why I would prefer you share the recording I already
Yes.
sent. But I stay here. Don't worry. Thank you very much.
Yeah. I hope you all can see. Now I'm going to start this presentation.
Good morning, ladies and gentlemen. It's my pleasure to share with you some knowledge we elaborate about the use and the reuse of recycling fine particles coming from construction and demolition waste. This is a very important topic, as we know that a large quantity of materials are produced that have to be recycled. This is a big problem if we consider the situation at the level of the entire world. We have a huge quantity of materials that are available and that could be recycled in a proper way in order to have new types of concrete or new types of mortars, at least to replace partially classical concrete. But the question is, what can we do with this type of material and how to manage it in order to be able to recycle them? First of all, we have to consider that we are living in a very, very limited world. If we consider the last COP in Glasgow, we can be sure that this limitation has to be considered in terms of energy, in terms of materials that are available specifically for building and construction industry, but we are limited also in terms of space. Where can we build? And in some countries, in some cities, it's very difficult to find a place to build again. We have also to consider a limitation of the capacity of the environment and the nature to be resilient. That means to be able to absorb the products and the waste products we are producing. And from this consideration, we have to change the behavior. That's one of the most important message we had from the COP in Glasgow. Regarding the construction industry, we have to consider the deposit and the market. Is it a good connection, a good correlation between the deposit and the market? That's what I would like to show you. Firstly, and then to consider the capacity of construction and demolition waste to be recycled, once again in the construction industry. In fact, if we are considering the scheme which is presented on the slide, we have to go from a linear economy to a circular economy, which is a well-known word specifically applied for the construction industry, and that has to be considered as an objective for the construction industry. Waste has to become a secondary raw material. If we consider the quantity of waste that are produced all over the world, we have in mind that about 4 billion tons a year are produced. It means from 80 to 126 tons per second, which are produced all over the world. The quantity and the quantity of waste which are generated by the human activities is enormous. 10 billion kilos waste which are annually produced. It corresponds in the construction industry to a quantity of about 200 million tons in 2015. And this construction industry is responsible also for the production of more or less 40% of the CO2 and more or less 40% of the total quantity of waste which are produced if we are added to recycled aggregates, for example, the quantity of earth which is produced as a waste. So this is enormous. On the other side, we need a lot of materials. As an example, the production of cement is about 4 billion tons a year, 56% coming from China and being consumed in China. And for the concrete industry, it corresponds to about 10 billion tons a year that we need to build bridges, roads, houses, buildings, dams, etc. In terms of production of cement and consumption of cement per inhabitants in 2018, it was corresponding to more than 1,700 kilogram in China. In the European Union, it corresponds to a average value of 300 kilogram. In the USA, it's a little bit less than this. And in Belgium, for example, it's 550 kilogram per inhabitants. This corresponds once again to this typical material, which is cement, to a production of CO2, which is representing between 5 and 8% of the world production. So we have to do something in order to reduce this production of waste. But we need material, we need construction material, we need aggregates. This is the production of aggregates in billion of tons in the European Union and the associated countries in Europe. So we annually produce about 3 billion tons of aggregates, which is also a material which is becoming more and more limited in terms of access to the exploitation of this type of material. So this production at the level of the European Union is coming from a lot of small quarries and pits which are operated by more than 15,000 companies and local companies, because this is a very particular way of production as it is located, and the transportation has a big impact on the cost of the material. So we are also limited in terms of transportation. This production of aggregates, you have here a view of the production and the consumption of aggregates. Production in this case in different European countries. Most of the production is coming from crushed rocks and sand and gravel, which are produced, and a very few quantity of materials are coming from recycled mobile or recycled fixed plants area. That means that there is a big challenge to develop and to increase the part of the use of recycled material in the construction industry. This objective is oriented according to the 3R theory, which is proposing a reduction, a reuse, and a recycling of materials. Recycling being the third step. Of course, it's better to reduce and to reuse before to recycle. But now we are at the level of recycling. What is it possible to do with this construction and demolition waste, which are already used mainly in sub-base and base material in the root construction, but which is a less noble application of this material. The objective being to introduce and to increase the use of this material in a more noble industry. It means concrete for prefabricated system or structural elements. The objective of the European Union in 2020 is that 70% of the construction and demolition waste should be valorized. Valorized means reused or recycled in the construction industry or in other industry if it's possible, of course. That means that our main objective is to reduce the use of classical and natural raw materials. For that, it's important to be able to characterize and to point out the difference between natural raw material and recycled raw materials. The process for obtaining recycled construction demolition waste is a 7-step process where we have the reception, the storage of the material, the first processing for separating most of the material, then a mechanical grinder that will come to the first main step, which is the crushing, usually by means of an impact or a jaw crusher. After that, there is a classification of a material, and specifically to obtain a steel and to extract steel, ferrous and possibly non-ferrous material from the mineral one, which are constituted mainly of concrete or bricks, ceramics, etc. A seventh important step is the separation, which is a manual separation of material to avoid to have rubber, to have wood, to have plastic material, which could be considered as contaminating material for the development and the production of aggregates. And finally, after a last mechanical grinder, we can obtain a recycled material with different types of granulometry, depending on the use which is coming afterwards. But the very important step is the primary crushing. This crushing may be obtained by mainly two types of crusher, like a jaw crusher, which allows to produce very fine fractions and can, however, induce a big wear process. That means that we will have to replace continuously the jaws in the system. The second type of crusher is the impact crusher that can be used to treat bulky waste like concrete slabs, etc., but doesn't allow to produce very fine particles and generally require a secondary crushing. How is it important to select the proper crusher? But this is important from the point of view of the characteristics and specifically the flakiness of the material. Here you can see that we produce experimental mixes, changing for one reference and one mix of reference concrete. We change type of cement, the type of material from SEM1 to SEM3, sandstones and not limestone. We also change the cement content and the water to cement ratio. And we wanted to investigate the effect of crushing on the characteristics of material. We can see here the flakiness index with regard to the granular fraction, and we may observe that the flakiness is indeed decreasing with the increasing granular fraction. That means that the jaw crusher is also producing flackier aggregates, even if there is no influence of the concrete composition. That means that, really speaking, the granular fraction has a big impact on the characteristics of the material we obtain, specifically with fine particles. We observe also that the water absorption, which is corresponding to the quantity of residual cement paste which is adhering to the former aggregates, is also higher for a lower granular fraction. That means that in sand particles we have a larger quantity of cementitious, residual cementitious material, which is detrimental, of course, for the characteristics of the material to be recycled. That's why we set up different PhD theses in order to study the characteristics of these fine materials. You can find the references on the slide, and these theses were oriented to the use and the recycling of crushed concrete aggregates, the influence of the residual gypsum, which is adhering to the fine aggregate particles, and also the reuse of bricks. I would like to focus only on the second and the third topic today. So first of all, what is the effect of gypsum residues of fine recycled aggregates? Recycled aggregates and specifically the finer fraction, that means the 0 by 4 millimeters, that the sandy particles are very often not valorized because they are corresponding to high quantity of residual gypsum. Gypsum is coming from the plaster, the gypsum which is used in the building, and gypsum is characterized by a chemical content of CaSO4 2H2O, which is and which can be detrimental in the reuse and the valorization of this type of material. The EN standard, which is devoted to the concrete, specifies that there must be a maximum of 0.2% in mass of sulfate in recycled aggregates. Why is it so important? It's because the chemical reaction of this gypsum with the calcium aluminate you can find in the cement in presence of water can produce big crystals in the forms of ettringite, and this secondary ettringite, which is produced by this chemical reaction, is producing expansion cracks, and by this internal pressure can induce very very big deterioration of the concrete. That's why there is a big and a strong limitation of the use of this material. The consequences at the structural level is this type of degradation with a lot of cracks, crocodile skin pattern cracks, which is induced by these internal pressure, specifically in structure which are in contact with the water. We made an investigation on different recycling plants, and we took some samples to analyze the quantity of sulfate contents. Remember that the limit is 0.2% of recycled aggregates. So in some situation, we were above this value or we were under this limitation, depending on the type of recycling plant and depending on the type of material which is coming to these recycling plants. Of course, concrete coming from roots construction doesn't contain a lot of sulfates, while concrete coming from houses is contaminated with larger quantities of this material. We try to study by recomposing materials in the lab to study and to define clearly the effect of the presence of this sulfate with the fine recycled aggregates that were used to produce mortar. And we measure the length change with the time of these different types of material. The observation was needed to have a high level content, here the reference with more than 3%, to obtain and to observe really length change, which is corresponding to internal pressure and cracking of the material. We try also to define the influence of different parameters. So you have here the evolution of the standard material, which was defined with a specific quantity of sulfate. Then we have the same material, but with a lower porosity, which is induced by a lower water to cement content, and a low temperature. That means the storage at the temperature under 5 degrees Celsius. These are the two main factors that may increase the expansion. The low storage temperature is favoring the production of thaumasite, which is another type of ettringite, and the low porosity doesn't permit the production of ettringite and doesn't let the ettringite to occupy a volume of voids inside the material. That means that with lower porosity there is a bigger internal pressure. If we are considering the effect of the content of gypsum or the high alkalinity of the media, we can observe a lower value of expansion, which is positive. At the same level, if we are using a high sulfate resisting cement, or if we are considering larger gypsum particles in order to defer the consumption of gypsum, or a higher porosity, there is a positive effect on the behavior of the material with a lower internal pressure. So finally, we can conclude that the limit, which was at 0.2%, is too restrictive, and we could go at least for the sulfate content of recycled materials up to 0.3%, and for a concrete where only fine recycled material could be used and natural aggregates, we could go up to 0.8% of sulfates without any problem. So these are the main conclusion of this investigation. These are investigations. The second type of material I would like to present to be reused is the brick fines valorization. Brick waste flow is corresponding to about 1 to 2% of the construction and demolition wastes. Bricks are actually recycled in terms of reuse for the construction industry, or the production of aggregates, or specifically brick fines, for example, for tennis area. But the brick fines remains a problem to be recycled. And the crushing of this brick is performed in order to increase the specific surface and to activate, by means of this fine crushing, the amorphous component of the material. That's what we try to do by a classical process into the lab, crushing by means of a jaw crusher, and then grinding by means of another crusher. We obtain three types of granulometries, B1, B2, and B3, corresponding to very fine, classical, and coarser particles. The classical one, B2, corresponding to the dimension of classical cementitious particle, and we try and we perform tests in order to study different percentages of substitution from 10 to 80%. The results clearly show that increasing the fine contents and decreasing the cement content will decrease the strength of the material. But, however, even with the 30% of substitution, compressive strength remains interesting. That means that we can find regular applications, specifically for B2, corresponding to a classical dimension for fine particles. We obtain still more than 60 megapascal as compressive strength after 90 to 180 days, which is interesting and corresponding to classical application in the concrete industry. The message is clearly that it's possible and it's quite easy to recycle construction and demolition waste fines in several applications, and we did it for concrete blocks, for 3D printing, for rammed concrete or prefabricated elements. What is important is to be able to characterize properly these fine particles before using them. I thank you a lot for your attention.